Hello everyone, I'm Guangwen Chen, a PhD student from the University of Manchester. Thanks to organizers for giving me this opportunity to share my work. My topic is the star formation in the center of NGC 1808 as observed by ALMA. Measuring star formation rate is one of the roots of astrophysics, and there are different ways to measure star formation rate. This is a schematic example of the star forming galaxies. And this sample includes stars with different ages, shown as various kinds of colors, and also include interstellar dust, shown as the brown background. One common way is to look at the ultraviolet continuum emission, because ultraviolet light can directly trace the young photonized stars, so as the blue point here. However, this kind of emission can be absorbed by dust, so it makes a bit challenging to use this star formation tracer in dusty star forming regions. We can also use optical and near-infrared hydrogen line emission to calibrate star formation rate. The widely used H-alpha line emission, for instance, because it can directly trace the photonized gas within the star forming region. But similar to ultraviolet continuum emission, this spectral line emission can be absorbed by dust as well, so it cannot be directly used in dusty star forming regions. Infrared emission from the interstellar dust is widely used to measure star formation rate as well. However, this emission cannot directly trace the young stellar population directly. In addition, dust can also absorb the light from the older stars, shown as the red points in the figure. We can use the radio synchronic emission to measure star formation rate because it is produced by the supernovae that form from the photonizing stars. However, this star formation tracer has some disadvantages. This emission originates from a more diffuse region than the star forming region. In addition, AGN can also contribute to this kind of emission. The conversion from the radio emission to star formation rate is normally based on the radiation between infrared emission and the radio emission, which could be very different. Each of the above star formation rate tracers has at least one typical disadvantage, but the free emission and millimeter hydrogen recognition line emission are different. As a star formation rate tracer, these kinds of emission have these two advantages over above limitations. It can directly trace the photonizing stars. Also, this emission is unaffected by dust obscuration. Therefore, comparisons of star formation rates from this emission with other star formation rate tracers can be used to examine the fundamental assumption behind these star formation rate tracers. Thanks to ALMA, even this line emission has been technically difficult for many telescopes. ALMA allows us to observe this line emission for the first time at high sensitivity of levels. For now, ALMA have been capable of detecting this line emission from some nearby galaxies. Since this method is very useful, and this sample is still very limited, we try to use ALMA to study starbursts in another nearby galaxy. The object we study is NGC 1808. It is a nearby buried spiral galaxy with a starburst nucleus. This galaxy is the sixth infrared brightest galaxy outside the local group in the southern sky. So it is an ideal object for us to calibrate star formation rate using free emission and recognition line emission with other star formation rate tracers within the central starburst of this galaxy. This is ALMA band 3 continuum image at the frequency corresponding to one of the recognition lines. The morphologies of the continuum emission in different ALMA bands are very similar. ALMA continuum emission shows that the star formation is mainly concentrated in the nucleus, and several other star forming regions which produce continuum emission detectable by ALMA. The image on the left shows where we measure the spectrum from our analysis. And the image on the right shows the spectral energy distribution, which is based on the combination of the VLA data and the ALMA data, where we have matched the beam size and maximum recoverable scale size so as to avoid the resolution effect. In the region that's covered the total detectable emission, which we have labeled T, we found that the total emission is free dominated within the ALMA band 3 data. If you go to the nuclear region, the emission is not as strongly free dominated. The fraction of free emission is about 65%. If you go to the southern region, then the fraction comes to 85%. According to this spectral energy distribution analysis, we can confirm that the central region of the NGC 1808 is briefly dominated in the ALMA band-free frequency, which means that we can use this briefly emission to calculate staff emission rate. Then we go to see the ALMA spectrum. The image on the right shows the spectrum of the hydrogen replication lines, H40 alpha and H42 alpha line emissions extracted from the T region. The velocity difference from the nuclear region and southern region produce a double peak line profile in the T region. However, we notice that there is a gap of the H40 alpha line emission compared to H42 alpha line emission. If we go to the spectrum from the southern region, we can see that both line emissions are significant. But if we go to the spectrum from the nuclear region, we can see that there's no significant H40 alpha line emission. It is strange that the H40 alpha line emission is only detected in the southern region, while H42 alpha line emission is detected in both. The first possibility is the low signal noise ratio for the spectrum at the H40 alpha line, which makes the line emission under the noise level. The second possibility we think is the H40 alpha line emission here is also contributed by a molecular line, CHCCCH. We also detected a strong CHCCCH line in the same spectral window. This blended line emission could possibly increase the signal higher than the noise level at this frequency. Even though the line emission in the nuclear region is unclear, the line emission measured in the T region and the southern region can be used to calculate the average electronic temperature with the free emission based on our STD analysis. According to the free emission with the electronic temperature, we can calibrate staff emission rate, which we show in the first two columns in the lab figures. We use this ALMA staff emission rate to compare with other staff emission rate tracers. We firstly compare the ALMA staff emission rate with the radio staff emission rate calibrated by 1.5 gigahertz emission. We can see that the radio staff emission rate is lower than the ALMA staff emission rate, which implies that 1.5 gigahertz emission seems to originate from a more diffuse region than the central starburst. Furthermore, the lower radio staff emission rate indicates that even if the AGN is present in the galactic nucleus, weak energy source, because the AGN can also contribute to the synchronic radiation, which means that if the AGN was strong, then the radio staff emission rate would be significantly higher than the ALMA staff emission rate, which isn't shown in our result. Secondly, we compare the ALMA staff emission rate with infrared staff, the total infrared flux and several infrared flux. The staff emission rate consistency between the ALMA staff emission rate and the infrared staff emission rate shows that the effect of the possible AGN on infrared emission should be weak, because a strong AGN can also contribute to the infrared emission as well. If the possible AGN was strong energy source in this galaxy, then the infrared staff emission rate would be significantly higher than the ALMA staff emission rate. As a consequence, young stellar population should be the main heating source for this dust. In addition, the trend of the staff emission rate from the 22 micron to the 160 micron implies that the fraction of the coal dust within this galaxy is low compared to nearby star-forming galaxy, especially for this point. We also show the continuum image on the right side, but with the large beam size of the infrared emission, we can only say that the extended structure for the 17 micron is similar to what is seen in the ALMA image. Then we compare ALMA staff emission rate with the H-alpha staff emission rate, which H-alpha staff emission rate have been corrected for the dust obscuration by adding a scaling term of a total infrared flux in this column, and then the rescaling term of 22 microflux in this term. And we can clearly see that the H-alpha plus infrared staff emission rate is significantly lower than the ALMA staff emission rate. This conversion fails in this situation probably because the central starburst in this galaxy is heavily dust obscured compared to the nearby star-forming galaxies, based on their total infrared flux to H-alpha flux ratio. We can also see this Mills H-alpha line emission image, which shows a more extended disk that includes more source of comparable brightness compared to the nucleus. Although combining H-alpha with infrared emission to calibrate star formation rate is widely used for many star-forming galaxies, it still needs to be used with cautions when applied it to dusty starburst galaxies like NGC, which could be more usual in the high-redshift universe. In the end, we compare the ALMA star formation rate with ultraviolet star formation rate, which have been corrected for the dust obscuration of total infrared flux and turned into micro-infrared flux. The low ultraviolet corrected using total infrared emission relative to ultraviolet plus 22 micro star formation rate is a consequence of the dust within the galaxy being relatively hot compared to more typical nearby star-forming galaxies, which is consistent with our results of the comparison of ALMA star formation rate with infrared star formation rate. We can also see the ultraviolet image is plotted here. We can see the brightest source in the ultraviolet image is a little offset relative to the galactic nucleus, which could arise from the high extension in the galactic nucleus or other young stellar population with the age of about 10 to 100 million years. And this is the summary of our work. In brief, ALMA can help us detecting more results and examining more assumptions using this excellent star formation rate tracer. Thank you.